This lesson introduces us to rotational kinematics for AP Physics C. Okay, we're going to talk about the various rotational variables. They have similar to our linear variables for distance, velocity, and acceleration. Then we're going to move quickly to our calculus view and the bridge equations. At the end, we're going to talk a little bit about slipping, what that is, as well as experimental situations. Okay, first off, just like in linear, okay, in linear we had the three variables at plus time of the displacement, velocity, and acceleration. We have the same concepts in rotational motion. Okay, so when an object moves in a circle, what's changing is its angle or its radians. Okay, and how quickly I move around this circle in terms of radians per second, and how quickly I change my velocity in radians per second squared. Okay, so I have three companion variables to my linear variables. They're all Greek letters: theta, omega, alpha. Okay, and what happens, not that we need to know this, okay, but the rotational variables effectively use a polar coordinate system where a point in space is defined as a radius from the origin or a distance from the origin, as well as an angle theta. Okay, spherical coordinates, if I ever get into third dimensions, would add a second angle phi. Okay, but it's still a vector, and we need to treat it, instead of I hat, j hat, it's now going to be r hat, theta hat. Okay, so in constant acceleration situations, okay, constant rotational acceleration, the theta, the alpha will be a constant number. And again, I can integrate alpha to get my rotational velocity, and I can integrate omega, my rotational velocity, to get rotational position. So velocity is still going to be radians per second, and acceleration is radians per second squared. So all of the same formulas apply, just with different letters, the Greek letter version. Okay, and all of these formulas are in, for the most part, except for the red ones, these formulas are in the formula sheet. Okay, but again, with calculus, acceleration no longer needs to be constant. Okay, so when that happens, we actually need to integrate and use our calculus knowledge to integrate the acceleration or the velocity to get the other variables. Okay, and so that brings me to the three bridge equations. Okay, these three bridge equations are frequently overlooked. The reason we need these three bridge equations is because they are key to solving many of the problems. Okay, because I frequently will not have enough equations to solve for the variables. Okay, but by bringing in the fact that my linear equations and my rotational equations increases the number of equations that I can use to solve my system of equations. So when the object rotates without slipping, and I'll talk about slipping in the next paragraph, in the next slide, okay, then these three equations are linked. Okay, my position or distance that I travel is equal to theta r, my velocity is going to equal omega r, and acceleration is going to equal alpha r. So I just take the Greek variables and multiply it by the radius of the circle. Okay, which kind of makes sense, because if I go one circumference of motion in my circle, I've gone 2 pi radians, and meanwhile my wheel has moved 2 pi r, or the circumference of that circle. Okay, and so everything is just multiplied by r. My angular is multiplied by r to get my linear equation. And that brings me to slipping. Slipping occurs whenever the object's rotational motion doesn't match its linear motion. Okay, in this case, the object is said to be slipping. Kinetic friction exists between the rotating object and the surface. Okay, and so an example of this is what happens when a car locks its brakes but continues to skid across the road. Okay, and so in this situation, the object could be spinning faster than its linear velocity or slower than its linear velocity. Both situations can happen, and I give you examples of both of them, either the tennis ball or the bowling ball. In either case, if the object is slipping, those three equations no longer apply. And we need to be a little bit cognizant of that as a possible error situation in experiments. Okay, if things are, if we're assuming that things are not slipping, but there might just be a little bit of slipping in there, we need to be a little bit careful. Okay. From an experimental standpoint, rotational kinematics experiments are going to be almost identical to the linear kinematics. Okay, I'm going to need to measure at fixed time intervals how many radians I've moved. Okay, and so again, instead of measuring distance, I'm measuring angles. Okay, same with velocity and acceleration. And what we're doing when we calculate those is average velocity between the two time points. The smaller the delta t, the better the approximation is going to be. Okay, thank you very much.